touch the x-axis. No, it will never get there because you can infinitely get closer and closer and closer and closer to the x-axis. When you get infinitely closer and closer and closer to something, you're never going to cross it. What are you approaching? What is that? It's an asymptote. Good. So what happens here is you wind up with an asymptote at your x-axis. Okay? It's going to get infinitely closer and closer and closer to it. It's never going to touch it. All right? Just like if you think about it along the lines is you can always cut something in half and keep going on and on and on. You're just going to get infinitely smaller and smaller and smaller. All right? Not so bad. So what we're going to do today is we're going to work on graphing this type of stuff. We're also going to have shifts to it, as well as working with what things are called compound interest problems, because this is all these are. It is. And it's really not that bad. Today we're going to talk about exponential growth. Tomorrow we're going to talk about exponential decay. For those of you guys that are in chemistry, you've probably done some of this stuff before. Anything with the E in it before?
No. Oh, gosh, yes.
So you can see exponential. Yeah, so it's kind of coincides with some of the stuff you guys are looking at right now. So for the next, what will happen for this chapter kind of entails two chapters again. We have exponential growth, exponential decay. Then we're going to start talking about logarithms. So there's a little bit of a mixture of both things. The way that I'm looking at how this first half is going to work out, we're going to do 8-1 today, 8-2 tomorrow, 8-3 Monday and Tuesday. Look at that, we're going to take 2 days for something. Yay. Then we'll quiz out on Wednesday for the first 3.
Next Wednesday.
Next Wednesday. And then we'll start with 8-4, because it's kind of a nice little break within the chapter. Just so you guys are aware of it, we'll start posting that stuff online. Yeah. It's not awful. You're going to be fine. All right, so we've done this, we've done this. Now, there's a generic form of this. There's always going to be a generic, yeah, your grade's reset. Right now, you guys all have 100%. Way to go. Yay!
Doesn't matter.
What happens here is that you have this generic form for exponential growth with non-shift. What this looks like is you get y equals a times b to the x. This value of a is always going to be your y-intercept. Always. Now, if you think about the problem we just had, we had y equals 2 to the x. What was the value of a that you did not see? 1. Very good. A lot of times they won't write it like that. They won't write it as 1 times 2. What you will see, though, is that you will see these written out like this. Y equals 2 times 3 to the x. They break it apart like that to tell you specifically what your a value will be. Does that make sense? So if I wanted to graph y equals 2 times 3 to the x, I already know one thing for certain. I know where my y-intercept will be. Where will it be? At 2. So let me show you how this is going to work. What was it? Y equals 2 times 3 to the x is what I wrote out?
Yep.
Okay. So if I want to start with this one, just to kind of get a rough idea of what this is going to look like, I know that my y-intercept is going to occur at my value of a. My y-intercept, or excuse me, my y-intercept will be at 2. Now let's think about what that means. If you think about why that happens, if your y-intercept is always when x equals what? 0. Think about how you got 2. It's 2 times 3 to the 0. Order of operations tells you to do what first?
The exponent.
Exponents. What's 3 to the 0? 1. What's 2 times 1? That's how you get your y-intercept there. Does that make sense? That's how that works. Now, is your value of a positive or negative? Positive. Positive. That means it's going to be working in the upward direction. If it was negative, it would be going the other way. It's very easy as we get through these things to see how this is going to work. Now, how in the world do you think you're going to figure out the next point? Plug and chug. All right, what's a very easy value of x to substitute in? 1. What's 3 to the 1?
6.
3. And what's 3 times 2? So at 1, it's at 6. Okay. If it was negative 1, If it was negative 1, it would be 1/3. Do you agree?
Yes.
So it becomes 2/3? Okay. So you think it's just kind of going like this, roughly. All right. That's kind of what we're looking at starting out with these graphs as doing. As we get in a little bit more complex, if you will, this becomes our parent function. Yes, sir.
Can you go over the y-intercept?
Y-intercept is always when your value is of x is 0. And if when you use your order of operations, if it's 2 times 3 to the x, it becomes 2 times 3 to the 0. Whatever that b to the x value is, it always becomes 1. So that value out in front of it, your a value, automatically becomes the y-intercept. Okay. So this becomes what we call the parent function. Now, if we have a parent function, that means what comes into play next? Could have been a daughter. The child function. We have a shift. So we're going to shift this. And remember when we shifted before, what letters did we use? H and K. What letters do you think we're using now? H and K. So now what's going to happen is we're going to take this a step further and do shifting with it. Y equals A times B to the x minus h plus k. Again, this becomes your horizontal and your vertical shift.
Does the minus mean opposite?
Yes. Just like it did before. Okay. It's very familiar to what you guys have seen in the past. We've worked with A, H, and K before. We did that with absolute values. We did that with parabolas. We did that with what else? Well, we've used it. We're going to use A, H, and K a lot. When we get into chapter 13 doesn't have much graphing, but chapter 14 is a lot of graphing. Chapter 10 is a lot of graphing. That's, again, lots of A, H's, and K's. So you're going to get really bored of A, H, and K. So again, what happens here is your H is your horizontal shift, and your K is your vertical shift. Yeah. It is kind of standard form, if you want to call it that. And the other thing that happens with your A, H, and K in this value, Y equals K will become your horizontal asymptote. If there's no shift, there's no K value, your asymptote's always going to be at 0, the x-axis. If there's a vertical shift, it shifts it to the new asymptote. All right? Not so bad? Let's try a couple. So I have the function 3 times 2 to the x minus 1 minus 4. When I start these problems out with A, H's, and K's, especially the first day or so, first couple of examples that I go through, a lot of times, again, I like to label out what everything is and label what everything means. It helps beat you in the head of what you're doing. I know that A is 3, H is 1, and K is negative 4. Just like you said earlier, it's the opposite value for your H, just like we've done in the past, and it's the same value for your values of K. So far, so good? All right. So when I go to graph these things, remember when we did the shift before we did a dotted, then a solid line? We basically do the same thing. With these exponential functions, all we have to do is basically plot 2 points on each curve and redraw your asymptote. So it becomes very simple. Yes, sir?
When you do the first one that's dotted, would you not use the H's and K's?
Correct.
And we just move them over to this happen? Okay.
That's exactly what we do. So if I do that without the dotted, if I'm using my parent function here, it would just be 3 times 2 to the x. Where is my y-intercept? 3. I first graph my parent of y equals a b to the x. In this case, it would be 3, times 2 to the x. I know that my y-intercept starts at 3. What's the next really, really easy point to plot? 1. What's 2 to the 1? What's 2 times 3? 6. I know it'll be at 1, 6. Where will the horizontal asymptote be for the parent function? At 0. So I know it's going to be, I've got this starting asymptote here.
Wait, how did you know that or what? Sorry.
I always know for the parent function, the asymptote will always be at y equals 0.
Okay.
And then all I can do is this. Oops, sorry. Like that. I'm just rough sketching what the curve would look like as a parent. From there, I now know the new graph is going to have a horizontal asymptote where? At -4. I know that this is all going to get shifted. Basically, everything's got to go down 4 and right 1. So all I have to do is move this point over 1 and down 4. Move this one over right 1 and down 4. I know my new horizontal asymptote is at -4. And now with the shifted graph, should I make it solid or dotted? Solid. So there it goes. And again, could you use table function to allow you to figure out if your 2 points are correct?
Yes.
Absolutely. Absolutely. One thing I will remind you though, if you do type this into your calculator, when you type your exponent into the calculator, you have to hit that button to the right to drop out of the exponent. I think you guys probably need that though, right?
Yeah.
It's easy to catch, yeah, it's all saying like, alright, that look great. But then again, you might not know what it looks like because you've never done it before. So who knows? Math is hard. Not so scary, is it? Not bad for the first day. Alright, let's try another one. Try this one. Take a second, try it. See how you do. Usually the graphing is usually very, very simple. Once you do a couple of them, it's like, oh, this is nothing. All right. After you do this one, then we'll jump into working with the word problems and compounding interest and things like that. And as long as you understand the vocabulary that we look at, those problems are very, very simple.
So is the box.
All right, so let's continue. Let's look at this. Again, in this problem here, your parent function, you have just 2x and the x minus 1 plus 3. What is my value of a that you don't see? Good. So your a value is 1, your h value is 3, and your k value is also 1. That means my parent function would be y equals 1 times 2 to the x. I know that I'll be at 1. And then if I use 1, I'll be at 2. Everybody okay with that? No. Now, from this one, yes, sir?
I'm confused on the second point.
I'm using this as my parent function. I'm picking anything that's easy to work with. 1.
What minus 3?
I didn't do that. I'm doing parent function first. Now, there's one of two things you can do here. When you go to shift this, all I have to do is move everything to the right 3 and up 1. So if I take these points, I just move them right and up. Or if I wanted to pick new values, I could do that as well. I suggest pick these and move them. Because now I know that where's my new horizontal asymptote going to be in? It's going to be at 1. New horizontal asymptote at x equals 1. If I take each of those points, go right 3, up 1. Oops. And then I have a new graph. And do you see how this wound up at 4, 3, just like we were saying? Works out just the same. Yes, sir?
Why is it always at 0, the horizontal asymptote?
what happens is it's never going to get, as you start looking at your exponents, the number of stuff, as your exponents gets infinitely smaller and smaller and smaller, as it's approaching negative infinity, it's approaching zero. Yeah, it's going to always be approaching zero. All right. Not so bad, is it? Yes, ma'am.
So on the graph, the delta looks from minus to the exponent like that?
Not the parent function. The parent function is always going to be your a, b to the x. Okay? And it's a quick shift. So let's look at this stuff now as far as growth models, growth factors. How this stuff, how you can use this in, I don't want to say almost so much like a real world, but into a problem that makes more sense.
It's in your math book.
In your math book, exactly. You guys will see exponential growth, exponential decay, what is that stuff? Radioactive dating, or not radioactive, carbon dating, is that right? Half-life? Is that one of those things? You use this, some of this stuff, some of this modeling stuff to get to those types of values. So at least that way you guys will know how to use this outside of the math classroom or what they're talking about when you get to chemistry or biology or something over there. So what we have here are what are called growth models. The value of A is always your initial amount. That's how much you start with, whether it's money, shoes, snowflakes. R is your rate. Well, I should say it's a percent, but used always as a decimal. Always, always, always as a decimal. So if it's 17%, what would be the decimal? 0.17, good. And then the t value is, it's got to be time, so we'll get to that in a second here. The junk inside the parentheses, the 1 plus r, that's called your growth factor. What'll happen here within some of these problems is that it'll write out a function for you, and it will ask you what is the rate. And it's very easy to distinguish what that percentage will be. And I'll show you an example here in a second. Well, I'll do this right now. For example, let's say you had y equals 3, 1.07 t, obviously different. What is your percent? 7%, very good. What happens here is that your percentage, the rate, if you will, your percentage is the decimal value here, because it's 1 plus the percentage. So in this example, my percent rate would be 7%. When we do exponential decay tomorrow, it's going to be 1 minus that, so we'll just do the opposite. Like I said, it's going to be fairly simple to see the differences here. So let me show you how this works as far as a problem is concerned. So what we have here is, here's our generic A. What happens here is that you have a population of some town in Nevada. That's not Vegas. It's modeled by the population function, 6191 times 20, 1.04 to the t. That's where t is going to be the number of years since 1990. So it's going to give you a starting point of where your t value is 0. 0 starts at 1990. If it's 2013, what would t be? 23. Well, it's 2014, so it'll be 24. Okay? That's the kind of thing that you're looking at being able to do. All right? So what they want you to do is figure out, well, what was the population in 1990? By what percent did it increase each year? So if I look at this, could I tell what my percentage of increase will be yearly for this town? It's 4%. Not 0.4, it's 4%. Everybody okay with that? Remember, because I'm looking at this value here, 0.04 is 4%. That's the rate at which it was increasing. Now, if they're asking you to figure out what was the initial population in 1990, what's your value of t? 0. Also, what's your value of A in this case?
6191.
6191, isn't it? Wouldn't that be your initial amount in 1990?
Yeah.
If you forgot that, if you set t equal to 0, what do you get for your value if you substitute that in? If I forgot how to do math, if I take 1.04 to the 0 power, what do I get? 1. What's 1 times 6191? So what's your initial amount? Okay, so we understand how growth model works then. Again, fairly straightforward. I forgot what I had to put here. Whee! Look at see-through.
Why couldn't we see through it before?
Do it again.
Jeez, that's it. She hangs out. TRMS?
Actually, I just thought
That's the opposite.
I know, I forgot today. I was talking about
Wait, what? This is not how you spell.
Anywho, so make it go away. Yes, I can bounce, right? Whee! All right. Now, in 2010, what would the population estimate be in 2010?
a number.
A number. Okay. What do you set your t value to be? If I'm saying
13,520.
I would set it equal to 20. Everybody agree on that?
Yes.
Yeah.
Okay. So in my calculator, again, all I'd have to do is 6191.
I got it. Currently we have a 20. We have a half percent.
Now, here's the thing. When you start talking about population growth and you have decimal values,
It's a midget.
it's it's not a midget. I would round it to halfway point, okay? 0.5 and up, you round up, just like you would normally. Round to the nearest whole person.
So midget's up down.
Couldn't you just like put it on the calculator?
You can do that as well. And use your table function, it works just the same.
Then it's 13,565.
Either way. Okay? Let's try another one. Another form that we use with exponential growth is bank accounts. Sure you guys like money, right? Of course you guys do. So let's see, we had y equals a. This is the growth factor. And this is compound interest. So here's what happens. In compound interest problems, you have your overall amount, that's what they call the value of A. Well, let's call that total amount. P is called your principal. How much you started with. You go to the bank, you open up a savings account, you got $300. Your principal is $300. Okay. The value of R, again, is your rate. So it's always a percentage as a decimal. So you always want to convert it to a decimal. We all remember how to do that, right? Let's move the decimal place over. The value of n. The value of n is the number of times it compounds. It's the number of times it's going to compound. For example, if it compounds annually, how many times does it compound? Once a year. If it compounds semi-annually, how many times?
Almost once a year.
Twice. If it compounds quarterly, 4 times. If it compounds monthly, if it compounds daily,
One time a day.
So that's kind of what we're looking. That's what it means. And again, it's going to be fairly easy to decipher how many times it compounds. So they're talking about it in terms of overall years. And then T would be number of years that you're having in the bank account. Okay? So, for example, let's use the analogy of a bank account. Let's say I go to the bank and I'm going to deposit my principal amount of $500 into a savings account that has a savings rate of, I don't know, what savings rate? It's 2.75%. I don't know if that's right. And then let's say that it compounds semi-annually. And I want to leave it in there for 20 years. How much will I have at the end? Now again, I just made up those values. What I want you guys to remember is how this stuff works. So in my calculator, I'm going to use the model. Principal times 1 plus rate over n to the t. Now, what's nice about my calculator with what you guys have now, if you use that alpha y equals, you can create the fraction bar, and you can type in all of that information right there. I could type in 500 parentheses 1 plus 0.0275 over 2 to the 20. I could type it in exactly like that if I use the correct button sequence. So let's see here, 500 parentheses. Wait.
It's a big number.
Wow.
In 20 years, I will have $657.03.
What in the heck?
Can we do it daily?
I thought you said it was NT.
What's that?
Because semi-annually is
Semi-annually is 2.
yeah,
Means it's twice.
and then it's n times t.
Oh, I forgot to have it up there. Sorry, I forgot to put that at the end up there. You're right. Sorry, I forgot the end value up there.
No.
Sorry. I wrote down the model wrong. Sorry, there's supposed to be a times 2 times 20. When I just wrote it out here, guys, I forgot to put the n times t for the exponent on the outside of the parentheses. So it should be times to the 40th power. Thanks for catching that. My fault. So just change your exponent to 40. 2 times 20. Okay. Do you know how to go back in your calculator to overwrite an entry?
Yes.
Hit second, enter, and it'll pull up what you just typed in, and then you can change by just using the back arrow. Hey, I got a little bit more money now. In 20 years, I'll have $863.38. I don't know if the bank will actually round up for you at 39 cents. I would imagine they wouldn't, because they want the money. You guys have all seen Office Space, right?
Wait, is that the one with the guy who talks about different
Hey, it's gonna burn down the building.
PC load letter. Anyway, what happens their scam that they were running had the same basic principle of how the interest is rounded out. Obviously, in your bank account, you're not going to have all these decimal values. It stops at, 20 cents, 30 cents, whatever. What happens to all those other decimals? Where do they go?
They disappeared.
They don't disappear. What they did is they were able to hack the code and take those little itty bitty decimal parts, and all of a sudden they had $1 million. And they thought they were going to go to jail. It's a great movie. I highly recommend it. Office Space. If you have not seen that, it is.
That guy who talks funny in the movie, is that actually how he really talks? Okay, that'd be weird.
Let's try another one. Take a look at this one, and I want you to try and see what happens within the 3 different possible compounding styles here. Okay? You have a deposit, you're putting $1,000 into an account that pays 8% annual interest. Find the balance after 1 year if the interest is compounded within the given frequency. Again, these are the values of n. If it's compounding annually, what's your value of n? 1. If it's compounding quarterly, and then daily. We're assuming it's not a leap year. Okay? So try that and just to kind of see how your values change depending upon the number of times things compound. Really not that big of a difference a lot of times. No. The leap year is on the presidential election years. So they get an extra day to blast us with ads.
I thought there's less days on
There's leap you're going further. So you have to get add a day.
Skip the day though.
You know.
Actually, technically.
You know Severino, Mr. Severino was almost born on a leap year. He was born on the February 28th, like really late in the evening. And it happened to be a leap year when he was born, so he could have never had a birthday. He could, no, actually I think he'd only be like 8.
You know, technically speaking, the year is technically 360.
You're never going to get your driver's license.
Oh, boy.
Oh, did they count that actually too?
Yeah.
That was so bogus. Like, what if your parents were like, oh, it's not your birthday this year, yeah, you know presents.
You could look at him and say, what? Oh wait, we're going to go soon. No, wait. What's the answer?
It's a difference of like $3.
Yeah, it's not that much, is it?
Kind of sucks.
It really is. Yeah. So when you guys start to get to the point where you have to invest money, you start to know how to mess around with some of these values. Okay? Again, exponential growth, the growth models. The difference between the growth model and the compounding interest. A lot of times the growth model doesn't have anything to do with money. Very easy to tell which one you're looking at. Okay. Let me give you a couple problems to try out. Try these, please. There are 6 graphs, I believe, I'm going to have you try. And then the rest of them are compound interest style problems. One thing I will show you. One thing I will show you here, when I put in the problems 43 through 54 all, within those types of problems, it's all kind of exponential growth. The growth model style problems, they're really not that easy to graph because the values are all messy. So if one of the questions says graph the function, don't do it. That's why I'm saying skip the graph problems. I think there's like 3 or 4 of them in the problems themselves. There's no need to look at the graphs of the growth models. Okay?
So if it says graph.
If it says graph for this chunk in here, if it says graph in that chunk, don't do it. Okay? There's like 3 of them that asks you to graph. Yes, sir. No, these are all like interest problems. Okay, those are all interest problems. Solving for one of the variables within the interest problem, so you might have to do a little bit of work on that. All right. But you want to know. Oh, wait, we have that.